Today on Macaulay Math, we're measuring the middle with mean, median, and mode. Intro. Okay, good day. I'm Professor Macaulay. This is Math 130, Intro to Statistics, lesson number 6 on measures of central tendency. Our goals for the day. We're going to find the mean, median, and mode of a population or a sample. We're going to find the weighted mean of a data set and the mean of a frequency distribution. We're going to describe the shape of a distribution as symmetric, uniform, skewed, then compare the mean, median, and mode for each. Mean, median, and mode all attempt to distill a data set down to a single value by picking a number somewhere in the middle. Mean is a mathematical average. Median is the exact middle point and is not affected by outliers. Mode is the value that occurs most often in a data set, which is very important when trying to find the most popular choice or when working with categorical data. These data points help statisticians summarize complex information. Let's get started. Definitions here. Where first, the mean of a data set is the sum of the data entries divided by the number of entries. So the population mean, which will be signified by the lowercase Greek letter mu, and it is the sum of the x values divided by the total population. And then the sample mean, which we're going to call x bar, is equal to the sum of all of the x values divided by the number in the sample. So again, this symbol is the lowercase mu, and this symbol right here is pronounced x bar. This symbol here is the Greek uppercase sigma, and it implies a sum. Again, n is the number of elements in the population, whereas lowercase n is the number of elements in the sample. The median of a data set of the value lies in the middle of the ordered data. The median divides the data into two equal parts. If the data set is even, then the median is the average of the two middle values. The mode of a data set is the entry that occurs the most often. A data set can have multiple or no modes. When two modes occur, the data set is said to be bimodal. And as a note, the TI-84 does not find the mode, but there is a workaround to find the mode in Desmos. Definition: an outlier is an entry in a data set that is far removed from the other values of a data set. For now, the eyeball test is okay, but we will have a formal way to find outliers later. Especially when you're talking about mean, the outlier usually throws off the mean by quite a bit. That's why when you talk about property values, they usually use median for property values, because if you have a bunch of lower priced homes in an area and then you have 2 or 3 that are like really expensive, it can throw the mean off by quite a bit. Finally, the mid-range is the average of the maximum and minimum value of a data set, but this is very rarely used. Okay, so this is the Desmos example for finding mean, median, mid-range, and mode for a given data set. And you've already seen the definitions, and we'll come back to them. But we're going to use Desmos to find these things and do it fairly quickly. And this is a reasonably small data set, only 20 elements long. First thing that we want to do if we're going to use Desmos to find the median, mid-range, and mode for the data set is we're going to go to Desmos. We're going to click on this add item, and just like most times when you're doing statistical analysis, you're going to start with a table of values. And so I am going to enter this data set here into my table there, and it is 28 and then 30 and then 28, 31, 31 again, 28, 33, 30, and then 38, 34, 34 again, 32, 27, 34, 28, 23, 18, and then 3 30s at the end.
All right, now we can look at the next line in Desmos, and I'm going to type in a command here. It's called length, Length. And again, you can see when it changes from italicized to regular type, you know you've typed in a correct command. And I'm going to go X1 here, and you'll notice it has 20 elements. And if we go back 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. And so as long as I didn't make any mistakes with my data entry here, I should be okay. And again, it asks us to find the mean, median, mid-range, and mode for the set. Now, Desmos does mean and median with its own command. And so if I go back to here and I type in mean and then X1, it will give me the mean of 29.85. And then if I hit enter and I go median X1, it'll go 30. So if I come back here and I go mean, let's see here, 29.85, and the median was 30. And I need to do my mid-range. Now, mid-range is not a command in Desmos, but if we go back to the definitions page and pull down here, the mid-range is the average of the maximum and the minimum value in the data set. Now, we can find those a couple of different ways. If I type in max X1, I get 38, and if I type in min X1, I get 18. Now, that's not the only way. And I'm going to show you another way in a later example where you can get a few of the other values, including the median, all together. But just for this example, I've got 38 and 18. So my mid-range is going to be the average of the largest and the smallest. And so since the largest was 38 and the smallest was 18, the average is just going to be the sum divided by 2. Let's do that real quick here in Desmos. And say parentheses, because we're going to do a calculation here before we do the division. We'll go 18 plus 38 all divided by 2, and we get 28 there. So my mid-range is 28, and then the mode. The mode is the element that happens the most often, and since this is such a small data set, we could go through and calculate the number of times a given element repeats itself. But since we are using Desmos and we would like to do a shortcut, there is no mode for Desmos. But if I do the dot plot that we did in the last lesson, and I go X1 again, and then I come down here and I do the automatic max, this shows you the dots for all of the values. Now, since mode is the element that occurs the most often, the value with the highest stack will be our mode. So since this element at 30 is repeated 1, 2, 3, 4, 5 times, that is going to be our mode. Okay, moving on.
Definition: weighted mean. Weighted mean of a data set whose entries have varying weights. The weighted mean is given by, so x bar, this mean is the sum of all of the x values times the weights that they are given, divided by the sum of the weights, where w is the weight of each entry x. Okay, so let's look at an example for how I'm going to use this particular function right there. So suppose you're taking a class where there are 4 different grading categories and each were weighted differently. Let's say that tests were weighted as 40% and your average on the 4 tests was 85%. Your midterm was weighted as 20% of your grade and you scored a 75 on that. Your final was weighted as 25% and you scored an 80. And then finally, your homework was weighted as 15% and you averaged 100% on those homeworks. Find your weighted average. So the first thing we're going to do is we're going to make a table. So I'm going to insert a table here. I need let's see here. I need 3 things. Yeah, I need a category, and then I got my, so I want to label the top. I want to have my 4 things plus a sum at the bottom. Let's go with that. Let's see. I think that'll be right. All right, so here I'm going to call this category. This I'm going to call score or average. And this one I'm going to call weight. And then this one I'm going to call, and so this one is my X. I'm going to call this, and this is going to be my W. I'm going to call this X times W. And so we have tests, we have the midterm, we have the final, we have homework. All right, so my score, I had on my test, my score was 85%. On my midterm, let's just put in the weight. So I've got the weight was 0.4. And then the midterm, let's see here, my midterm was weighted as 20%, and I scored a 75. So the score there was a 75 and 0.2 for that one. On my final, I did a little bit better. We did an 80, and that one was for 25%, so 0.25. And in the homework, we did 100, and that was worth 15%, so 0.15. And so if I add these up, because I weighted as percentages, and it doesn't have to come out this way, it doesn't have to come out that way. You can weight it however you want. But since we did it as percentage of a total grade, it should come out to be 100. So 4 and 2 is 0.6. 0.25 and 0.15 is 0.4. 0.4 and 0.6 gives me a sum of my weights, sum W equal to 1. But that doesn't always have to happen. And so we want to calculate X times W, so just the value in the score column times the weight. So let me do that. I'm going to do that separately. So 85 times 0.4, that gives me 34. And then 75 times 0.2, that gives me 15. And then 80 times 0.25 is 20, and then 100 times 0.15, I don't need a calculator to do that, just move the decimal place twice, right? So 100 times 0.15, which should just be 15, and then the sum, let's do a better job, of X times W would be this sum here, so 34 plus 15 plus 20 plus 15 is 84. So my X bar is the sum of X times W over the sum of W, which in this case was 84 over 1, or 84%. You get a B for your final grade there.
Okay, so let's say you wanted to do this example using Desmos. Now the Desmos version is going to look very similar to the version that you did when we did it by hand. So you're going to see a lot of similarities here, and it's pretty easy. And for this example, the by hand version is probably just as easy as the Desmos version, but if we needed to do a large weighted mean where there were a lot of categories, you might use Desmos for that. So let's go through it step by step. And again, it's going to be very similar. So I'm going to open up Desmos, and again, I'm going to have a table. And for my X values, that's going to be my score and my average. My Y values will be the weight. And then we're going to make another column here. And that's going to be the new thing for this particular example, is that you can have multiple columns. You don't need just X's and Y's. So if you remember back, and you can look at your notes, the test average was an 85, and then the midterm average was a 75. The final was an 80, and then the homework you got 100. So in this column, I'm going to put the weights just like I did in the handwritten example. 0.4, and then 0.2, and then 0.25, and then 0.15. Now I'm going to come over to this third column, and we needed the x values times the weight values. And what's cool about Desmos is it's going to let you just define that in that top portion of the column. So I'm going to go x1, and then I'm going to go time, so shift 8, and then y1, and you'll see that it does all of those calculations for you. If you check your notes, 34, 15, 20, 15, those are the values that you had. And so I'm going to come back over here, and I'm going to remind you that the weighted mean was the sum of the values in that x times the weight column all over the sum of the weight. Now, how do I get Desmos to do the sum? Okay, well, that's new. So what will come down into the next line, and what we need is to get the sum of the x1 times x2 columns. Now, sum doesn't work, but if you type TOTAL, total, and then parenthesis, and we're going to get some fairly complex titles to our columns. So I'm going to get into this mode where I'm going to highlight it all, and I'm going to copy. So I'm going to go Control C, and then I'll come back down here to the total and go Control V, and it will paste whatever was in that column. And again, we get the 84, and if I wanted to do the total of that second column of the weights, I could go just Y1, and it was 1 again, so it's not a big deal. And then, so if I want to get that mean, and we had 84 divided by 1 gives me 84%. So that's a nice, quick, easy way to use Desmos to do some work. And again, if you've got to do repeated calculations, set up a table and let Desmos do the grunt work for you. Okay, moving on.
So we're going to finish up this section with talking about data and how data is distributed. And we're going to come up with some names of graphs, and then I'm going to go over the definitions here, and then in the next screen we will draw some pictures that kind of match up. So first we got symmetric data. If the data is symmetric, then the distribution of the data to the left of the mean approximately mirrors the distribution of the data to the right of the mean. Uniform data, a set of symmetric data where each class has approximately the same frequency. Skewed data, data is going to be skewed to the left if one tail of the data is elongated to the left, and data is skewed to the right if one tail of the data is elongated to the right. So let's take a look at what some of this stuff means. And so first, let's take a quick look here at symmetric data. So if I put, and we're going to call that little green dotted line the mean value, and if I wanted to draw in symmetric data, essentially I'm going to get a value so that when I look at what's on the left side, I am going to approximately get the same thing on the right. Now it's not going to be perfect, but we're going to get essentially the same thing. Now, uniform data is still symmetric. It's still going to give us something that looks where it's the same on the left as it is on the right, but what we're going to end up getting is data that is going to be the same frequency at each level. Skewed left and skewed right are a little bit different though, and so when they say it's skewed left, the tail is going to be elongated to the left. And so if we talk about this first symmetric, this is a tail over here on the left-hand side, and this is a tail here on the right-hand side. So if data is going to be skewed left, then that tail on the left-hand side is going to be skewed, or is going to be elongated. So what we're going to get is a graph that's going to kind of look like this, because that tail over there is elongated. Now, is that in skewed left data, the mean is actually going to be a little bit to the left of the median. So the median is the point that's in the middle, and so the amount of data on the left hand side and the amount of data on the right hand side are going to be the same. But the median is going to be a little bit over here because it's elongated to the left. And when you have skewed right data, the skewed right data is going to have a tail that's elongated to the right. And that's all I got for today, folks. So
Today's Marvel fun fact of the day: in the original Thor movie, we see a glimpse of a completed Infinity Gauntlet during the scene where the Frost Giants break into Odin's vault. To reconcile this break in continuity, Cate Blanchett's character Hela decries it to be a fake when it appears again in Thor Ragnarok, like 6 years later. So that's all I got today, folks. You have a good day. Goodbye.